The official story is simple enough. During the 19th century, industrialization spread through Europe and North America as nations learned from one another, shared technical manuals, and sent engineers abroad to study best practices. By the 1840s, infrastructure projects across continents began to reflect similar methods: standardized rail gauges, comparable bridge designs, uniform waterworks. Knowledge diffused through books, blueprints, and trained professionals traveling between capitals. But here's the friction. Between 1820 and 1850, public works projects in Philadelphia, Manchester, St. Petersburg, and Calcutta began requiring identical skill sets. Not just similar approaches, but the same specific expertise in hydraulic engineering, masonry arch calculations, and gas distribution networks. The Erie Canal, completed in 1825, demanded knowledge of lock mechanics that wouldn't appear in published engineering texts until 1834. Manchester's sewer system, begun in 1846, used techniques documented in French manuals that weren't translated into English until 1851. The Croton Aqueduct in New York, finished in 1842, required Roman-style arch construction that American engineers reportedly had no formal training in. The projects happened before the training could. The methods arrived before the manuals. The expertise existed, but the documented path to acquiring it didn't. And it happened everywhere all at once, as if the knowledge had always been there. This is a documentary exploration of that timing. We're not presenting conclusions. We're examining what the records show, what the structures reveal, and what the timeline suggests when you place it all side by side. Some call this evidence of inherited systems from an earlier period, a label that's come to be associated with the term Tartaria. Others see natural diffusion moving faster than documentation could track. Either way, the pattern is there. Let's start with what we can measure. In 1811, construction began on London's Regent Street. The project required engineers who understood load distribution across multi-story facades, underground drainage integration, and coordinated gas line installation, a combination of skills that wouldn't formally exist as a unified discipline for another 2 decades. The project proceeded anyway. No records explain where the engineers trained. No schools taught the combination of knowledge required. By 1817, Baltimore began constructing America's first gas streetlight network. The system required expertise in coal gas production, pressurized distribution, and underground pipe sealing, techniques that British engineers had only just begun experimenting with in isolated trials. Baltimore's network was operational by 1821. The British manuals describing the full process weren't published until 1823. In 1825, the Menai Suspension Bridge opened in Wales. It was the longest suspension bridge in the world. The engineer, Thomas Telford, had no formal training in suspension dynamics, because no such training existed. He designed the structure using principles that wouldn't be mathematically codified until the 1830s. The bridge still stands. The same year, Russia began constructing the Nicholas Canal, linking the Volga River to the Baltic Sea. The project required knowledge of large-scale lock systems, embankment stabilization, and hydraulic cement mixing, all techniques that had been used in isolated projects across Europe, but never documented in a single comprehensive source. Russian engineers implemented them flawlessly. These weren't experimental projects. They were large-scale public infrastructure built with precision and durability. They didn't fail. They didn't require extensive revision. They worked as if the knowledge had already been tested, already been refined, already been applied at scale somewhere else. But where? In 1837, Isambard Kingdom Brunel began construction on the Great Western Railway. The project required engineers who could calculate gradient tolerances for steam locomotives, design bridges capable of handling distributed weight loads, and construct tunnels through inconsistent geology using techniques that wouldn't be formally taught until the 1850s. Brunel's railway opened in 1841. It ran on time. By 1842, the Croton Aqueduct was delivering 90 million gallons of water daily to New York City through a system of Roman-style arches, underground tunnels, and pressurized distribution networks. The chief engineer, John Jervis, had no formal training in aqueduct construction. He studied ancient Roman systems and reportedly replicated their methods. But Roman engineering text had been lost for centuries. He built it anyway. The same year, Hamburg began constructing a centralized sewer system using principles of gravity-fed drainage and separation of waste channels, techniques that wouldn't be standardized across Europe until the 1860s. The system was operational by 1845. In 1848, London began replacing its old water mains with a pressurized distribution network capable of serving a population 3 times its current size. The project required expertise in pipe metallurgy, pressure regulation, and flow calculation, skills that weren't taught in British engineering schools because those schools didn't yet have formal civil engineering programs. The network was completed by 1855. This is where the timeline starts folding in on itself. The infrastructure appeared before the institutions that were supposed to teach how to build it. The expertise existed before the formal education. The systems worked immediately, consistently, across multiple continents, as if they were following a blueprint that no one admits to having. In 1851, the Crystal Palace was constructed in London for the Great Exhibition. It was the largest glass structure ever built. The engineering required an understanding of modular prefabrication, load-bearing iron frameworks, and thermal expansion coefficients, concepts that were still being debated in academic circles. Joseph Paxton, the designer, was a gardener. He had no formal architectural training. He built it in 9 months. By 1854, Philadelphia had completed a centralized water pumping station using steam-powered hydraulic systems that mirrored designs being used simultaneously in Paris, Liverpool, and Hamburg, cities with no documented exchange of technical plans. The systems were identical in function, comparable in scale, and operational within years of one another. The official explanation holds. Knowledge traveled through books, through visiting engineers, through correspondence and shared technical societies. But the speed troubles the narrative. The precision troubles it more. Because this wasn't rough adaptation. This was exact replication of techniques that hadn't yet been written down. And it raises a simple question. If the knowledge was being invented as these projects were built, if engineers were genuinely figuring this out for the first time, why does none of the infrastructure look experimental? The United States offers the clearest view of the pattern, not because the anomaly is stronger there, but because the timeline is compressed. Between 1820 and 1860, America built infrastructure designed for cities that didn't yet exist, using methods that shouldn't have been available, at a scale that exceeded any immediate need. Start with the Erie Canal. Completed in 1825, it stretched 363 miles across New York State, connecting the Hudson River to Lake Erie. It required 83 locks, each built to identical specifications. The canal's engineers needed to understand hydraulic cement mixing, a technique that allowed concrete to set underwater, a process that had only been rediscovered in Britain in 1796 and wasn't yet commercially produced in America. They needed to calculate precise lock dimensions to handle boats that didn't exist yet. They needed to design a drainage system capable of managing seasonal flooding across terrain that varied from marshland to bedrock. The chief engineer, Benjamin Wright, had no formal training. He was a surveyor. He learned on the job, or so the story goes. But the canal didn't fail. It didn't require major reconstruction. It functioned immediately at full capacity, as if the design had been tested before. By 1830, the Baltimore and Ohio Railroad was under construction. It was America's first commercial railroad, built before American engineers had ever seen a functioning locomotive in operation. The project required knowledge of gradient engineering, bridge load calculations, and rail metallurgy, none of which were taught in American institutions. The chief engineer, Jonathan Knight, reportedly studied British rail systems through correspondence. The railroad opened in 1830. The British engineering manuals describing those systems weren't published until 1832. In 1837, construction began on the Croton Aqueduct to supply New York City with clean water. The system was designed to deliver 90 million gallons per day, enough to serve a population of 500,000. In 1837, New York's population was 300,000. The aqueduct wasn't built for the city that existed. It was built for the city that would exist 20 years later. The design required Roman-style masonry arches spanning valleys, underground tunnels carved through bedrock, and a gravity-fed distribution network that maintained consistent pressure across varying elevations. John Jervis, the chief engineer, had built canals, but never an aqueduct. He studied descriptions of Roman systems and replicated their methods. The aqueduct opened in 1842. It required no significant repairs for 50 years. The same pattern appears in Britain. Between 1830 and 1850, British cities began constructing centralized sewer systems, gas distribution networks, and pressurized water mains, all at scales that exceeded their current populations. Manchester's sewer system, begun in 1846, was designed to serve 400,000 people. Manchester's population in 1846 was 250,000. The system used separated waste channels, gravity-fed drainage, and brick-lined tunnels built to tolerances that wouldn't be standardized until the 1860s. The engineering knowledge required for these projects, hydraulic gradients, pressure regulation, underground construction techniques, wasn't formally taught in British universities until the 1850s. The Institution of Civil Engineers, founded in 1818, didn't establish standardized training programs until 1840. Yet the infrastructure built before 1840 matches the quality and precision of everything built after. Liverpool's dock system offers another example. Between 1815 and 1835, Liverpool constructed a series of interconnected docks with hydraulic lock systems, warehouses designed for cargo volumes the city wouldn't handle for decades, and underground rail tunnels connecting the docks to the city center. The tunnels were built using techniques that wouldn't appear in British engineering texts until the 1840s. The docks were designed to accommodate steamships that were still experimental in 1815. By 1825, the system was operational. It handled more cargo than any port in Europe, not because Liverpool's trade had grown, but because the infrastructure had been built assuming it would. This is where the American and British timelines converge. Both nations were building for futures they couldn't predict, using methods they weren't supposed to have, at scales that exceeded any rational economic justification. And both nations were doing it simultaneously, often using identical techniques, identical materials, identical design philosophies. In 1842, Hamburg began constructing a centralized water system using pressurized iron pipes, filtration stations, and distribution networks that mirrored systems being built in London and New York. There's no record of technical exchange between the cities. The systems appeared independently within years of one another, built to the same standards. By 1848, St. Petersburg had completed a gas lighting network using the same coal gas production methods, the same underground distribution techniques, and the same pressurized regulation systems being used in Baltimore, Paris, and Manchester. The Russian engineers had no documented contact with their Western counterparts. The systems were identical. This isn't diffusion. Diffusion is messy. It's iterative. It produces variation. When knowledge spreads naturally, you see experimentation, failure, adaptation. You see projects that don't work. You see engineers testing different approaches in different cities, learning from mistakes, refining methods over decades. That's not what the infrastructure shows. What the infrastructure shows is uniformity, precision, immediate functionality. Systems that worked the first time, built by engineers who weren't supposed to know how, in cities that didn't yet need them. Consider the scale. The Erie Canal moved 3.8 million cubic yards of earth, by hand using horse-drawn carts and basic excavation tools. The project was completed in 8 years. The Panama Canal, built 80 years later with steam-powered machinery, moved 232 million cubic yards of earth and took 10 years. Adjusting for technology, the Erie Canal's rate of earth movement is comparable to projects built a century later. The Croton Aqueduct required tunneling through solid bedrock using black powder and hand tools. The tunnels were bored to precise gradients, maintaining a consistent downward slope of 13 inches per mile across 41 miles. Modern tunneling projects, using laser guidance and mechanized boring equipment, aim for similar tolerances. London's sewer system, constructed between 1859 and 1875, used 318 million bricks, 880,000 cubic yards of concrete, and hand-excavated 82 miles of tunnel beneath a functioning city. The system was designed by Joseph Bazalgette, who calculated flow rates, pipe diameters, and pumping station capacities for a population of 4 million, double London's population at the time. The system still functions today, serving 8 million people. These weren't experimental projects. They were final designs, implemented at full scale with no precedent. And here's the deeper friction. The administrative structures required to manage these projects. The procurement systems, the labor coordination, the quality control, the documentation, were as sophisticated as the engineering. The Erie Canal project managed over 9,000 workers simultaneously, coordinated material deliveries from multiple suppliers, and maintained consistent construction standards across 363 miles. This required accounting systems, communication networks, and hierarchical management structures that didn't formally exist in American industry. The same systems appeared in Britain. By 1830, British railway companies were managing construction contracts, labor forces, and supply chains using administrative methods that wouldn't be taught in business schools for another century. They were using standardized contracts, competitive bidding processes, and project management hierarchies that modern corporations would recognize. Whether this reflects inherited knowledge or rapid parallel development, whether it represents continuity with older systems or the sudden emergence of new ones, the timeline compresses the possibilities. Because all of this happened within a single generation. And it happened as if the blueprint already existed. The term Tartaria appears on European maps between the 16th and 19th centuries as a geographic label for the vast interior regions of Central Asia and Siberia, territories that European cartographers knew existed but had limited information about. It wasn't a unified empire. It was a catch-all term for areas outside direct observation, populated by various Turkic and Mongol peoples. By the mid-1800s, as Russian expansion filled in the blanks, the label disappeared from maps. In recent years, the term has been reinterpreted. Some use it as shorthand for a hypothesis, that the infrastructure we've been examining, the aqueducts, the rail systems, the administrative coordination, represents inheritance rather than invention. That the 19th century wasn't building from scratch, but rebuilding, repurposing, or completing systems that predated the official timeline. Others interpret the same evidence as natural acceleration, the result of industrial momentum, cross-continental information exchange, and economic pressure creating synchronized development. Knowledge moved faster than documentation could track. Engineers learned through informal networks, on-site training, and direct observation rather than formal education. A third perspective suggests the timeline is correct but incomplete, that the infrastructure doesn't represent mystery, but rather the underdocumented reality of how large-scale projects have always functioned. That precision and scale have always preceded formal theory. That engineers have always known more than the textbooks captured. All three interpretations address the same evidence. None require supernatural explanations. All remain within historical possibility. Return to 1816, the year without a summer. Volcanic eruptions in the Pacific caused global crop failures, mass migration, and economic collapse. Within a decade, infrastructure projects began appearing across Europe and North America at unprecedented scale. Canals, aqueducts, railways, gas networks, systems designed not for recovery but for expansion. Whether this represents opportunistic rebuilding of older foundations or the rapid emergence of new industrial capacity depends on which framework you apply. The evidence supports both. The timeline accommodates both. When we use the term Tartaria in this context, we're not claiming a lost civilization. We're using it as a label for a pattern. Infrastructure that appears over-engineered for its moment, expertise that arrives without documented training, administrative systems that function before the institutions teaching them exist. It's a way of holding space for the observation without forcing a conclusion. The infrastructure remains. The precision remains. The timing remains. Whether it reflects inheritance, convergence, or something the historical record hasn't yet clarified, that's the question the evidence invites, not the answer it provides. The 19th century built systems that still carry water, still bear weight, still function as designed. They were built by engineers whose training isn't fully documented, using methods that weren't yet standardized, at scales that exceeded immediate need. That's not speculation. That's measurement. What it means, whether it points backward to older systems or forward to sudden capability, depends on how you interpret velocity, how fast knowledge can travel, how quickly expertise can emerge, how much precision is possible without precedent. The pattern is there. The rest is interpretation.